Section 13.3, Hamilton Paths and Hamilton Circuits. In this section, we'll learn about understanding Hamilton paths, Hamilton circuits, and complete graphs, solve traveling salesman problems. A Hamilton path is a path that contains each vertex of a graph exactly once. Compare that to the Euler paths that we learned about last week, where we went through each edge one time. This time we're going to be going through each vertex exactly once. The graph below has a Hamilton path AB, so if we go from A, B, C, E, D. There's also another one goes from C, B, A, D, E. Can you find others, or are there others in this graph? And here's another graph, has a Hamilton path ABC, FH, EG, D. And again, there's another one listed there, and you can find some others in that. Determine two different Hamilton paths in the following graph, and this is a multiple select question. So what you want to do is go through each option and see whether or not it makes sense. Remember, the Hamilton path goes through each vertex exactly one time. And if you check on choice A, it starts at A, D, F, G, H, E, C, B. That one works. Choice B also works. A, B, C, E, D, F, G, H. That one also works. Choice C, if you notice, choice C goes through vertex D twice, so we can't use that one. And choice D goes through vertex C twice, so that's not an option. So the correct answer here is A and B. A Hamilton circuit is a path that begins and ends at the same vertex and passes through all the other vertices exactly one time. This graph has a Hamilton circuit A, B, C, E, D, A. Can you find another? There are others in that particular graph. This one has a Hamilton circuit A, B, D, G, E, H, F, C, A. Begins and ends at the same vertex. Determine two different Hamilton circuits in the following graph, and there's 4 choices given. Now first we can eliminate choice B because it starts at A and it ends at G, and remember a circuit has to start and stop at the same vertex. So let's try A. A starts at A, E, C, F, D, G, B, A. That one works. We already eliminated B. How about C? C goes from, if you follow it along, from G to F, and there is no edge between G and F, so we can't use C. D will work. You can go ahead and check that one. And E doesn't go through F. It should say does not go through F. So the correct answer here is going to be A and D. A complete graph is a graph that has an edge between each pair of its vertices. Determine a Hamilton circuit for the complete graph shown below. So one is A, B, C, D, E, A. And there's many others on that one. The number of unique Hamilton circuits in a complete graph is n minus 1 factorial, and the factorial is a shorthand notation that says take that number times 1 less, more, etc., etc., etc. So if it was 3 factorial, it would be 3 times 2 times 1. So let's take an example. American Idol travel. Keith Urban, Jennifer Lopez, Harry Connick Jr., and Ryan Seacrest, the cast of the American Idol, are in Hollywood, H. They want to travel to the following cities to judge contestants' auditions: San Antonio, East Rutherford, Birmingham, Memphis, and Seattle. In how many different ways can they visit each of these cities and return to Hollywood? So we want to say, here's the graph, here's the complete graph. There's a path between every 2 vertices. And there's 6 vertices here, 1, 2, 3, 4, 5, 6, and remember the formula, and the edges are going to represent the one-way flights between those locations. We're going to come back to this graph in a minute. Determine the number of Hamilton circuits. So it's 6 minus 1 factorial, which is 5 factorial, which means 5 times 4 times 3 times 2 times 1, which gives us 120 different Hamilton circuits. So there's 120 different ways they can start in Hollywood and visit all 5 cities and return to Hollywood. A traveling salesman problem, we have a complete graph that represents cities and the process of traveling between those cities. And the goal in a traveling salesman problem is to find the least expensive or shortest way to visit each city once and return home. In terms of graph theory, our goal is to find the Hamilton circuit with the lowest associated cost or distance. The Hamilton circuit with the lowest associated cost or distance is called the optimal solution. And we're going to go over two methods, the brute force method and the nearest neighbor method. And we need to have a complete weighted graph. That's a complete graph with the weights, the numbers, either the prices or the distances listed on the edges. In the brute force method, represent the problem with a complete weighted graph, then list all the possible circuits for the graph, and then pick the one, determine the cost associated with each circuit, and the Hamilton circuit with the lowest cost or distance is the optimal solution. So let's try an example using brute force. Priya is the chief operating officer for the Hard Rock Cafe. Priya lives in Orlando and needs to visit Hard Rock Cafe restaurants in Atlanta, Memphis, and New Orleans. The weighted graph for the problem is shown below, and these are the cost of the flights between the various cities. She will start in Orlando because that's where she lives, and she has to visit those other offices. So there's a total of 4 vertices we see here. So there are 4 minus 1, or 3 factorial, 3 times 2 times 1, which is 6 possible unique Hamilton circuits that we need to look at for cost. Now, when it's a small problem like this, it's not too difficult to go ahead and list out all the circuits and all their costs, and we have all 6 here. And we notice the lowest cost happens to be $545 for 2 of these circuits, which actually turn out to be the reverse of each other. And these are shown on this map here. So here we start in Orlando, we go to Atlanta, New Orleans, Memphis, back to Orlando, or we reverse the trip. We go from Orlando to Memphis to New Orleans to Atlanta and back to Orlando. So those would be the minimal cost, the optimal solution for Priya to visit those cities. The nearest neighbor method is a way to find an approximate solution for a traveling salesman problem. And these can be used where the optimal solution determination is not reasonable. There's just too many circuits to calculate. And so what you do here is you have your complete weighted graph. You identify where you want to start. And then of all the edges that connect to the starting edge, choose the one that has the smallest weight, either the shortest distance or the lowest cost. Travel along this edge to the next vertex and continue the same process. And then eventually get back to the original vertex. So we're going to do this with the American Idol problem that we had with the 5 cities. And here's the cost of travel between those Hollywood and those 5 cities is shown in this little table here. And so here's the complete weighted graph, and there's all the prices on the graph that we took off of here. And so what we want to do is we want to start in Hollywood, and where are we going to go first? We want to pick the edge with the lowest cost. And if we look across all 5 of those, we will see going to S, which is Seattle, is the lowest cost, $180. Now we're in Seattle, and where are we going to go from here? We want to pick the next edge that has the lowest cost associated with it, and we see that actually is going to take us to San Antonio. Now from San Antonio, we don't want to go back to Hollywood. We want to go to one of the 4 remaining locations that we haven't been to. 3 locations, either East Rutherford, Memphis, or Birmingham. And it looks like this time it's going to be Birmingham at $274. So now from Birmingham, we're either going to go to Memphis or we're going to go to East Rutherford. And East Rutherford has a lower cost, $258. And then finally, there's only one city left, and that's Memphis. And then from Memphis, we go back to Hollywood. And then we go ahead and we add up all those costs, and we come up with a grand total of $1,007 for this method using the nearest neighbor. Now, if you do all the circuits, which you can do with a computer program, you'll actually find that there's one that's a little bit lower at $965. And we would not find that using the nearest neighbor method, but using the brute force method, we would have found that. So it's a little bit less. So the nearest neighbor does not always give us the optimal solution that comes out of the brute force method. Section 13.4, trees. A tree is a connected graph in which each edge is a bridge. So on the left side here, you'll see examples of trees. On the right side, you'll see examples of graphs that are not trees. In the ones on the right side, there are many edges that still can be removed and create still a connected graph. So they're not considered to be trees. The ones on the left side, every single edge there, if I remove it, I'll create a disconnected graph. Determine whether the graph is a tree. If it is not a tree, give a reason why. So here we have an edge between A and B, but then we have vertex C with no connection to A or B. So this is not a tree because it's not a connected graph. The answer is C. Use a tree to model the parent-child relationships in the following problems. So we have a woman, Paloma, who has 3 children, and we see that in all the graphs, and their children are Sherry, Laurie, and Kevin, and we see that across all the graphs also. And then it tells us that Sherry has 1 child, Dolores, Laura has 1 child, Betty, and Kevin has 1 child, Hopalong. So we want to look through the graphs here. Sherry has 1 child, Dolores, and if we look at graph A, we don't see a relationship shown in the graph between Sherry and Dolores, so we can eliminate figure A. We also don't see a relationship there between Laura and her child, Betty, so that one wouldn't make sense either. Laura has 1 child, Betty, and in graph B, it shows Laura having 2 children. That's not correct. Graph C shows that child B is shared between Laura and Sherry, and that's not correct. So graph D must be the correct graph. A spanning tree is a tree that is created from another graph by removing edges while still maintaining a path to every vertex. And let's look at an example. Kutztown University is considering adding awnings above its sidewalks to help shelter students from the snow and rain when they walk between the buildings on campus. A diagram of the buildings and connecting sidewalks where the awnings will be added is on the next slide. So here's the campus and here's the walkways, and we want to put awnings over those so the students will be protected. We don't necessarily have to cover all the walkways because that would be very expensive. That's what the president originally wanted to do. So now the president's proposed to place just enough awnings over a select number of sidewalks so that by moving from building to building, the students would still be able to reach any location without being exposed. So the first thing we want to do is represent this situation with a graph, and then we want to create 3 different spanning trees from the graph that would satisfy the president's proposal. So here's what the graph looks like. So we have the administration building, and then we have the other buildings shown here, and these are the walkways. The edges represent the walkways between the buildings. Now, from that particular graph, we can create many spanning trees. So we could create one where they'd always have to start in the administration building, and then the walkway to each of the other buildings would be covered. That would be one spanning tree. Here's another possibility. Start administration building, then you'd have to go through the tech building to get to these 2 buildings. Here's another possibility. It's really going to determine, actually we're going to go through this in a minute, when we look at the cost of putting in the awnings. So let's take a look at, so determine a spanning tree for the graph to the right. So what you want to do here is take edges out while still maintaining a path between every pair of vertices. And if you notice here in C, there's 2 vertices with an edge here that are not connected to the rest of the graph, so we can eliminate that one. And B still has some edges that could be removed. So the correct answer of the one shown there, this is not the only spanning tree, but of the 3 given, this is the only one that would be a spanning tree for that given graph. The minimum cost spanning tree is the least expensive spanning tree of all the ones under consideration. And we use Kruskal's algorithm to help us work this out. Select the lowest edge on the graph first, then select the next lowest edge graph that does not form a circuit with the first edge, and continue with that process until you've connected all the vertices. And then you'll have the minimum cost spanning tree. So the Colorado Park and Recreation Association wants to build bike trails that will connect the cities of Aurora, Boulder, Denver, Englewood, and Golden. The approximate distances in miles between those cities are shown here. And we're going to use Kruskal's algorithm to determine the minimum cost spanning tree that would link each city and create the shortest total distance for the bike trails. And then we're also going to work out the cost of the bike trails if it costs $5,500 per mile. So first thing is just put 5 dots down to locate the 5 cities. It doesn't have to be done to scale. Now we want to say, where do we want to start first? So we look at the distances here, and we see the shortest distance we have is between Aurora and Denver, right here, 9 miles. I'm sorry, 8 miles is shortest first. Englewood and Denver. And then actually it happens that Aurora to Denver is the next shortest. It doesn't always happen that the first 2 will be connected through a common vertex. Now from here, we still have to connect in Boulder and Golden somehow. And so now we look and we see, well, where would we want to go next? So if we look, we take a look at the distances. The next shortest distance in this whole table past the 8s and the 9s that doesn't form a circuit with the edges we already used is 16 here between Golden and Denver. Now we still need to get Boulder in here. So we take a look and we see, what do we have for Boulder that we might be able to use? And if we look at the Boulder distances, we see the 26 is the next one that we could use, and that would connect Boulder to Golden with a distance of 26 miles. And so there's our complete spanning tree with the distances. Now to figure out the cost, we add up the total miles, we come up with 59 miles of trails, and we were given a cost of $5,500 per mile. So the total cost to complete this bike trail is amazingly $324,500.